If you look at our modern energy infrastructure, it is tempting to think we have found the finish line. Simply covering enough land in wind turbines and solar panels would seem to solve the climate crisis. But that grid-first approach hits a wall when looking at how the global economy actually moves. Sectors like transoceanic shipping and commercial aviation and steel manufacturing operate on a physical scale that makes standard electrification impossible. This chart compares volumetric energy density. Batteries drastically underperform liquid jet fuel, taking up too much room. Scaling up triggers an exponential weight penalty. To power a jet across an ocean, the required batteries become too heavy to carry cargo or even move. Because of these strict physical limits, heavy industry relies on highly concentrated combustible chemical bonds. These machines require a fuel source that provides massive power in a lightweight package. You cannot fly a Boeing 777 or sail a massive container ship on the transient flow of electrons from a battery pack. These machines strictly demand physical, energy-dense molecules. This creates the defining tension of modern energy. We generate an abundance of clean, renewable electrons, yet the pillars of global trade remain structurally dependent on fossil-based molecules. Bridging that gap requires us to rethink the purpose of the power grid. By viewing renewable electricity as a raw manufacturing tool rather than a final consumer product, we unlock new industrial possibilities. Wind and solar farms generate vast amounts of power, but they peak unpredictably. When they produce more electricity than the grid can use, that excess power needs a destination. This is where electrolysis enters the process. It acts as the mechanical bridge between electrical physics and chemical manufacturing. In this process, we route an electrical current directly into water. The force of the current strikes the water molecules, violently breaking the bonds and splitting the oxygen atom away from the hydrogen atoms. This isolates pure green hydrogen. By breaking the molecular bonds, we effectively trap the kinetic energy of the renewable electron directly inside the newly freed gas. Through this step, we achieve something once considered impossible. We translate transient electrical energy into a stable, combustible physical form. Hydrogen gas is powerful, but it is difficult to store on an aircraft or cargo ship. Heavy industry needs dense liquid fuels. To create a liquid hydrocarbon, we need one final ingredient. That ingredient is carbon dioxide. We can capture it directly from the exhaust stacks of heavy industrial plants or pull it from the ambient air. This schematic shows the final phase, molecular synthesis. Inside a reactor, green hydrogen and captured carbon dioxide are subjected to intense heat and pressure, forcing them to bond together into long, complex hydrocarbon chains. The direct outputs of this process, sustainable aviation fuel, green methanol, and synthetic hydrocarbons, are chemically identical to the fossil fuels we pull from the ground. Because these fuels are synthesized using carbon that was already in the system and powered by renewable energy, they create a closed loop. Burning them in an engine simply returns the captured carbon to the atmosphere without adding new emissions. A moment of wonder. By bonding these elements, we have successfully locked the energy of the sun and wind inside a synthetic liquid molecule. This chemical reality enables long-haul jets and ships to run on incredibly dense liquid fuels without pulling new crude oil from the earth. This reveals a profound chemical irony. Carbon dioxide, once civilization's most dangerous industrial emission, is transformed here into a highly valuable raw material for the next industrial era. The economic implications extend to the geopolitical map. By synthesizing fuels domestically using their own renewable grids, nations can drastically reduce their structural dependence on imported oil. Industrial decarbonization functions as an aggressive economic engine, creating new industries and intellectual property, while lowering emissions as a secondary benefit. The next industrial era will be defined by the chemical building blocks we forge from power, shifting the priority from how many gigawatts we generate to how we use them. If every renewable electron carries the potential to be forged into a molecule, electricity becomes the raw material of our civilization. It is the first step in a much larger industrial process.